Okay, so what we did this morning is we determined some actions, first of all, from somewhere in the 1991 suite of codes. We then used EN 1990 to convert those characteristic actions into ultimate actions. We applied them to the frame somehow, so maybe we did some modelling of the frame. We would have included those equivalent horizontal forces. We would have calculated alpha crit to see whether second order effects are significant or not, and if they were significant, maybe we would have used that amplifier to allow for second order effects. So finally, at the end of that process, we have the design effects. So that would be things like the design bending moment and the design shear and the design axial force. And now we are going to verify members against those design effects. So the first thing we need to do is we need to calculate the resistance of the cross section. And before we start calculating the resistance of the cross section, we need to classify the section. So section classification, we're into our main Eurocode now, 1993-11. Classification comes in section 5. So here is some helpful symbols. I think the Eurocode has some very good parts to it. So one thing which I think is very good, certainly compared to UK practice, is that I can understand W for web and F for flange. So I'm always very clear about what the Eurocode is talking about. An ordinary diagram, which to you in the Ukraine might be absolutely straightforward. To us in the UK, there is a little bit of excitement because we are used to the major axis being the XX axis and the minor axis being the YY axis. So for us in the UK, this is quite a change actually, and you will be surprised that many structural engineers are annoyed that the axes have changed. And I think there are more complicated things in life than just changing the axes. This is why we are going to classify. At one level, we are going to classify because when we open up the code, it will give us a different rule for a different class. So class 1 and class 2, we follow a certain rule. Class 3, we might follow a different rule. So if you like, at its most basic, we are classifying so we know which rule to follow. More fundamentally, the classification is a reflection of the behaviour of the member. So this diagram is for beams in bending. So on the bottom axis we have rotation, and on the vertical axis we have resistance. And there are two resistances shown. One is the plastic resistance, one is the elastic resistance. You can see the formulas here. It's simply a modulus. So W elastic is the elastic modulus, WPL is the plastic modulus, multiplied by yield. So class 1 sections then will get at least to the plastic moment of resistance, but then the special thing about them is that you can rotate them a long way before the resistance starts to drop. Class 2, you can get to MP, but you cannot rotate it very far before the resistance starts to drop. Class 3 will get to the elastic moment of resistance somewhere in between elastic and plastic. Class 4, sadly, has got elements which are so thin, which means that it doesn't even achieve the elastic moment of resistance. And those, I think, would be the stress blocks that you would be familiar with from your college days. So class 1 and class 2, a fully plastic stress block. Class 3, some people call this an elastic stress block. Class 4 This is how the Eurocode deals with a Class 4 section. This area is in tension, the top of the diagram is in compression. The Eurocode says there are some stable parts of the web. It's stable in this zone because it's next to the flange. It's stable in this zone because it's next to the tension part of the web. And the Eurocode says you can calculate those lengths and then neglect the rest of the web. The web is still there. So this is not how you deal with beams with a hole in. So the web is still there, it's just that we've chosen to neglect it. Personally, I would avoid Class 4 because when you neglect part of the web, you change the position of the neutral axis. And then later, if you come to apply some compression down this member, you apply the compression at the centroid of area, which is eccentric to the neutral axis. So later on, there will be some additional moments that you need to take care of. I think that's complicated, so me personally, if I found a section was Class 4, I would choose another section. I don't like Class 4 sections. So within the code then, having classified, there are then different rules that apply to different sections. So if we're thinking about compression, for Class 1, 2 and 3, we will use the gross area. Class 4, we will use the effective area. And in bending, we'll use the plastic modulus for Class 1 and Class 2, elastic modulus for Class 3, and we could do something clever if we wish to for Class 4 sections. Remember, if your beam is fully restrained, so the compression flange is not free to buckle, then the resistance of the cross-section will simply be a modulus multiplied by a yield. Very, very straightforward. When we classify then, many of the classification limits depend on epsilon. And you will see epsilon there. It's the root of 235 divided by your steel grade. And for you, if you're using S235, of course, epsilon will be 1. For other grades of steel, it would have a different value. Perhaps, if you are in your workbook, you could turn right to the back, and there are some pages which have a letter and a number on the top of the page, and perhaps you would look at page B1. Perhaps you won't look for page B1 because I see that in your handbook you don't have them. Perhaps you would like to open this excellent publication instead and look at page 40. So page 40 is talking about internal compression parts, and that would be webs normally. An internal compression part is a web. And then you'll see that there are 3 columns. One is a part subject to bending, that's the left-hand column. The middle column is for a part subject to compression, and the right-hand column is for parts subject both to bending and compression. And you'll see that there are simple limits, and they concern the C over T ratio. And from the diagrams at the top of the page, you will see the C dimension is indicated. The C dimension, in technical terms, is the flat part. So simply, you look at the length of the flat part, you divide by the thickness, and you compare to those limits For example, for a member in bending, the limit is 72 epsilon. If your C over T ratio is smaller than 72 epsilon, then you will have a class 1 web. So generally we would think about the webs, and then perhaps if you look at page 41, we would also think about the flanges. Most of the time, when you look at page 41, we will be in the left-hand column. That's a drawing of the compression flange of a beam, and it feels compression maybe because it's got axial compression, or maybe because it's a beam subject to major axis bending. Either way, the compression flange feels uniform compression. The other two columns, they are for if the member is being bent in its minor axis, and then it would depend whether you have compression or tension at the tip of the flange. If you fall outside a class 3 section, then you would be a class 4 section, and you would need to look at EN 1993 part 1 subpart 5. So as soon as you are not class 3, then you are into an entirely different part of the Eurocode. If you look back at page 40, on the right-hand column, you will see the diagrams that look like this. So in the right-hand column, a part subject to bending and compression, we would need to consider alpha, perhaps, and we would need to consider psi. The formula for alpha and psi are not given in the Eurocode. And I wonder how that can be, that something so important, we're not told how to calculate it. And this is one of those areas where different countries have different views for how this should be calculated. But for today, ladies and gentlemen, I would ask you to acknowledge that the UK knows best. And therefore, today, we will use these particular formula. If you were in Austria or Germany, they would not like these formula at all. If you were in France, they are very happy with these formula. So I hope in the Ukraine, you will be happy with these formula. You will need them later on because you are going to do a numerical exercise. So on your page 41 looks something like this: major axis bending, left-hand column, and the two right-hand columns are for minor axis bending. So if we were classifying an I section, for example, with two flanges and a web, we would look at the web, we would look at the flange, and the classification of the whole section is the highest class from either the web or the flange. If you are looking at page 41, if you look at these formula here, there is no alpha, there is no psi here. The limits on page 41 are only geometric limits. The level of stress does not appear in those formulas. Okay, so we classify them, and we know whether we're class 1, 2, or 3. So when we are calculating the resistance, we know that perhaps we're using the gross area or the effective area. If we're calculating the bending resistance, we know that we're using the plastic modulus or the elastic modulus. So really that's what we've just done. We then need to multiply by some strength. You might say the yield strength. For the moment we'll just call it strength. And then we need to divide by a partial factor. So first of all, steel strength. Within 1993, we have two options when we consider strength. The two options are that we can use the product standard, so that would be the standard that covers plate, or the standard that covers rolled sections. We can look in the product standard and we can determine the yield strength from the product standard. Or another option is that we can use table 3.1 from the Eurocode. And you'll see the highlights here. The national annex may give the choice. There is table 3.1, and it's relatively attractive because it's simple. So table 3.1, perhaps that would be our choice. I looked in the Ukraine standard, and the Ukraine national annex says that both approaches may be used. So to me, on that particular issue, your national annex is not very helpful, because the Eurocode says you can do whatever you wish. The national annex says you can do whatever you wish. In the United Kingdom, we say you cannot use table 3.1, you must use the product standard. So today, ladies and gentlemen, we will use the product standard. So when you look in the product standard, the strength is based on the thickness. Today, we will base our strength on the thickness of the flange. I know that the web may be thicker, but my practice is always to look at the thickest part of the cross-section, and that will provide the measurement for the strength of the complete cross-section. So perhaps I am a little bit conservative. There is a screenshot of the product standard. This is actually for rolled sections and for plate. And perhaps of interest is that the strength steps down at 16 mil, 40 mil, 63 mil, and 80 mil. So in the product standard, there are more steps than you would find in table 3.1. If I go back just for one moment, you will see it's either smaller than 40 mil or greater than 40 mil. The product standard always has many more steps: 16 mil, 40 mil, 63 mil, 80 mil, and so on. Today, we'll take our strength from the product standard. So there will be some area perhaps, or a modulus, multiplied by a strength divided by a material factor. And from the Ukrainian national annex, these are the material factors. For the next few minutes, ladies and gentlemen, we are dealing with cross-sectional resistance, so we will be interested in gamma M naught. Later, when we get on to buckling resistance, we will be interested in gamma M1. But for the moment, gamma M naught. So we're going to do some calculation and then divide by a value of 1. And you might say, why have we bothered to divide by 1? It makes no difference at all. And the answer is that that recommended value may change over time. So in my first presentation this morning, I said that the Eurocodes are subject to revision even now. And there is a suggestion that gamma M1 might become 1.1, or perhaps 1.05. So I make the point because you ought to be aware that over time, some of these values may change. Now, if you would like to turn to the page that follows page 88, you'll find a classification exercise. And I would like to classify this member, because then we are going to follow this member for the rest of the afternoon and tomorrow morning. This is fabricated from plate, 2 flanges and a web. We need to classify it. then we're going to work out the cross-section, and later on we're going to work out its buckling resistance. So I believe that all the data is there for you, and armed with page 40 and 41 of this guide, I believe that you will be able to classify this particular member. We want to know what class it is, so that then we know, are we using the gross area, the effective area, the plastic modulus, or the elastic modulus. So I believe that if you work through step by step, and it follows onto the second page here, I believe that you will find the correct answer. We have been considering, or we are in the area of cross-sectional resistance. And for cross-sectional resistance, when we carry out a calculation, we're generally going to be dividing by gamma m naught. Later, we will be interested in gamma m1 for buckling of columns, for lateral torsional buckling of beams. The other value here, gamma m2, 1.25, is used in the situation which I have drawn on the flip chart when something is in tension. So here I am imagining a piece of flat steel, piece of steel plate. Perhaps it is being used as bracing, and this would be a bolted connection. And there are two checks to be done. So if you could have a look in page 43 of this book. If you are in this book on page 43, you will see section 6.2.3. And then number 2 is a check of the cross-section, which is the area multiplied by yield divided by gamma m naught. And that's a check of the gross cross-section, and it's using gamma m naught. Gamma m naught is 1.0, so we would check the gross cross-section. But in section 3, you'll see there is another check to be done. 0.9 multiplied by the net area, multiplied by the ultimate strength, but notice this time it's divided by gamma m2. And that's where you would use gamma m2, 1.25. You tend to use it with the ultimate strength. So the second check would be to check the net area. So the gross area minus the diameter of the holes, you would use it with the ultimate strength, but divided by gamma m2. So for things in tension, like bracing made out of flat plate, that's where you would find gamma m2 being used. So cross-sectional resistance then, there are a few clauses concerning cross-sectional resistance, and we're not going to look at them all, because they are not very interesting. We know that, for example, things in compression, they will fail by buckling rather than by cross-sectional resistance. We are very interested in cross-sectional resistance in bending if the beam is fully restrained, because then the bending resistance is the cross-sectional resistance. When you look through the clauses, you will find expressions that cover the case when you have high shear, because if you have high shear, you cannot enjoy the full moment resistance. The Eurocode gives you the von Mises interaction, so I think many people will recognize this interaction. And the Eurocode says you can use this expression if there are no clauses that cover your situation. So, for example, there are clauses that cover shear and moment. there are clauses that cover axial compression and moment. And it's recommended that you use those clauses, mainly because the Eurocode calculates the resistance for you. And the resistance is normally a plastic resistance. So it assumes that stress has been distributed all over the cross-section or the area or the modulus. A plastic resistance, whereas this interaction is always elastic. It's adding together elastic stresses and therefore will be conservative. So if you come across a situation where the Eurocode does not give you a clause to cover your particular circumstances, then the Eurocode says you can use the von Mises expression. So in terms of cross-sectional resistance, we always want the resistance to be greater than the applied force or the applied moment. If we are in tension, as I drew on the flip chart, we will generally check the gross area using the yield strength and gamma m naught, and we will also check the net area using the ultimate strength and gamma m2. In compression, if it's class 1, 2 or 3, we will use the gross area. If it's class 4, we will use the effective area. And in bending, we will take the appropriate modulus. Class 1 and class 2 would be the plastic modulus, multiply that by yield, and that will give us the bending resistance. If we were in other classes, then we would use a different modulus. Shear resistance may well be important, so there is a formula to calculate the shear resistance. You will notice that the PL in this formula, a plastic shear resistance. You know that actually if you drew the shear resistance or the shear stress, you will know that there is a parabola. Well, the Eurocode is going to give us a plastic shear resistance. So a shear area multiplied by yield divided by √3. We're in cross-section, so divided by gamma m naught. And I think many people will recognise the √3 from the von Mises formula, or you may well remember from your college days, principal stresses. I learnt something called Moore's stress circles. Okay, 1 or 2 people are nodding. And you will find √3 in those expressions. For a fabricated section, conservatively, you would just take the shear area as the height of the web multiplied by the thickness of the web. But you could do a little bit better than that. So if you turn to page 45 of this guide, you will see a formula for fabricated members, I think that says, where there is a 1.2 factor in front of it. And that would be okay up to grade S460 steel. So to assume that value is 1, and therefore just take the height of the web multiplied by the thickness of the web, that would be conservative. If you follow the advice in this guide, you could increase the shear resistance just a little bit. In my view, shear resistance is not usually critical, because a member will probably have been designed on the basis of the bending resistance or probably the deflection. And if bending or deflection governs, then usually shear is not critical. Unless you have a point load very near the support. In that case, shear may be critical. For rolled sections, the shear area is rather more complicated. That's the shear area there. We in the UK think that this is a very pedantic way to calculate the shear area. We think this is unnecessarily complex. In the UK, we always said that the shear area for a rolled section is the thickness of the web multiplied by the overall height of the section. And when we use that area, we find that the answer is only 2% different from this rather more complicated approach. This is the rule for high shear. High shear is defined when the applied shear is more than 50% of the shear resistance. So if you have that situation, a high shear more than 50% of the resistance, then you must calculate the bending resistance based on a reduced design strength. But in my view, high shear is relatively uncommon. I'm always surprised when I come across high shear. You can either calculate a reduced design strength, so here it is, a set of formulas, or you can calculate a reduced resistance directly. There is other helpful guidance around pages 46 and 47 of this guide, which gives you information about when you can ignore axial load, for example. So if the axial load can be carried on the web alone, then you can leave the flanges to carry the bending moment. And you see how that is represented in some of these formulas. You've got the height of the web multiplied by the thickness of the web. So there are some simplifications in the Eurocode, and generally you'll find those on pages 46 and 47. I feel uneasy about talking too much about cross-sectional resistance because, in my mind, it's almost always buckling which will be critical. I know we have to check cross-sectional resistance, but normally other things will be more important. So if we have something which has an appreciable length, then compression will be critical if we're designing a strut. And if our beams are unrestrained, the compression flange is free to move, then lateral torsion or buckling will be critical. And I say again, in my experience, I generally find that shear is not critical.